So we're going to use this example to just recap what we did last lesson. Can anybody tell me what this reaction is known as?
The Haber process?
Yes, that's right, yeah. Manufacture of ammonia, which is really important for fertilizers. So what will be the effect if I come along and I increase the concentration of N2? Which way will my equilibrium shift using Le Chatelier's principle?
To the right.
Brilliant, yeah. So we can say equilibrium shifts to right-hand side to remove the added N2. So you need to say which side it shifts to and why. So it's shifting to the right-hand side to remove the added N2. What about if I change that? If I increase now the pressure of, increase the concentration of NH3, what will happen? Yeah, equilibrium will now shifts to left-hand side to remove the added NH3. So you've got to be really careful when you answer the questions. You've got to explain really clearly why it's happening. And finally, what will happen if I increase the pressure? What do I need to look at? I need to look at total moles of gas on the left and the right. So what's my total number of moles of gas on my left-hand side?
4.
Yeah, brilliant. 4 moles. 1 nitrogen, 3 hydrogen. Remember, you're only looking at the big numbers. Brilliant. How about ammonia?
2.
2.
So we'll move from high to low pressure.
Yeah, so which way will it shift?
Shift to the right.
Brilliant, yeah. The equilibrium shifts to right-hand side, which has fewer gas moles, so reduces the pressure. We can use Le Chatelier's principle now to work out the effect of changing the temperature on the reaction. First of all, before you do anything, you have to identify whether the reaction is end or exothermic. So what is this reaction? This is exothermic because it's negative. So it's exothermic. What I recommend you do is once you've identified that, pop on your equation. So that means that this direction is exothermic, which means that the opposite direction is endothermic. So if you just think a note of that, the way it's shown, delta H, it tells you for the forward reaction, that's exothermic, which means the reverse must be endothermic. So, using Le Chatelier's, can we predict which way will it go? So, if the temperature is increased, which way? So, increase in the temperature will shift a reaction in the, what do you reckon? If we increase the temperature, what does the reaction want to do from Le Chatelier's principle? That's rate, it's going to increase the rate, but what will it do in terms of the equilibrium position? Will it shift to the left or to the right? It will shift for this one, it will shift, so which direction does it shift? It will shift in the endothermic direction, so it shifts in the endothermic direction. To reduce the temperature. If you think about it, it does make sense.
Yeah.
I increase the temperature, the reaction goes, oh, he's making me hotter. What can I do? So he's going to go in the endothermic direction, which to you feels cold, doesn't he? He absorbs the energy, so he gets rid of it. So if I now do the opposite, if I decrease the temperature, we'll do the opposite. So decreasing the temperature will shift a reaction in the exothermic direction. The reaction tries to produce heat energy to increase the temperature. So in this case, for this example that we've just done, if I increase the temperature, it will shift to the left-hand side. If I decrease the temperature, it shifts to the right-hand side. But it really helps you if you just label it. As soon as you see it, label it, which is exo, which is endothermic, and then it allows you to clearly see which way you're going to shift. So we do a simple practical. This is our equilibrium. We're going to decide whether this direction is exothermic or endothermic. And we've got two differently coloured cobalt species. Now this equation may look a little bit weird. You think, oh, what's going on? We deal far more, this is what we call a ligand substitution reaction, which we look at A2. At the moment, all you need to know is that it's a reversible reaction that we're going to look at. So I've got some pretty cobalt here. Cobalt's beautiful. Fortunately, very toxic, but never mind. So, there we go. So I'm going to put a spatula of this lovely purpley cobalt complex, and we're going to make up a mixture of 10 centimetres cubed of water and 10 centimetres cubed of concentrated hydrochloric acid. So mixture of water, acid to the water. So let's do 10 of water. And then we're going to do 10 of concentrated acid. So give it a mix, and then I'm just going to pour that into this. So this will all dissolve up, like so. Right, and we need to give that a stir. A stir? A stir. A stir. And we will get that to dissolve up. So we're going to now place it in some ice water, and we'll wait for a few minutes to see what happens. But can you see it's quite a nice pink, dark pink colour at the moment? Okay. So here I go. I've got my nice pink solution there. We're going to bung him in the hot water now. So he's nicely cooled down. He's been in ice, nice and cold. Let's bung him in the hot water, and we will see what happens. So I will just pop him on there, and hopefully you will see he's changing colour. Can you see at the top he's gone blue? Look, you may want to come close, come close. He's definitely going blue. Can you see around the edge there? I'll try not to go. If I just bring him out, you see he's gone blue? Yeah? You happy? Yeah, you're not bothered. Yeah, we believe you. Okay. Don't make us move. We're nice and comfy. Okay, so we'll leave him there. Precariously perched, but hopefully, as we leave him in there, you can see that he's definitely gone a blue colour. So, I've heated him up and he's gone blue. So, which direction did it go when I heated it? It went from pink to blue. So when I heated it up, it went in that direction. When I heat a reversible reaction up, which direction does it go in, the exo or endothermic direction? It goes because it wants to absorb that energy, doesn't it? So we're going to say that this direction is going to be the endothermic direction. So if I cool it down, it should go in the exothermic direction. So let's swap them around and we'll give that a go. So I'll take my blue complex out. You can definitely see that's blue. And I'm going to pop him in to the ice. And let's see if we can get that to cool down nicely. Maybe take a few minutes to work that one. So we've had him cooling down for a few minutes now. We've said that when he cools down, if you cool something down, it goes in the exothermic direction. So he should have gone pink. Has he gone pink? Can you see that's definitely pink colour? Yeah, happy. That is a pink colour. Yeah, okay, cool. So he has gone in here. So this direction is therefore the exothermic direction because I cooled it down and he went pink. So that's the way you can tell which way is exo and which way is endothermic.